locally, and I will start recording there. Okay, so this is week 6 somehow. We've got 2 hours today and we've got 2 hours tomorrow. So what I want to do is to introduce some new material to go with the assessment today. Try not to talk for too long, but I do find that I go slower than I expect when I'm talking to the box in front of me. So I'll introduce some new material and give you some time to get on with it. And then tomorrow what I want to do is, hopefully people will have asked questions. We can go through some material. I've got one request to go through Gauss-Jordan elimination method. So I'll go through that. Any other bits that people ask that people would like me to go through, I'm happy to do it. Just drop me a request either in the chat or email. What I'll do, perhaps one way of doing that is, if you saw the email I sent earlier, that I put a link to this gather room. So after I've given a talk, I'll go in there, and then I don't know if anyone's explored it. Let me see if I can find the email. So in there you can wander around and find me. I've not got the camera on because I can only have the camera on in one place. So only 25 people can get in there, but I suspect it won't be a problem. So I'll be sat over here somewhere you can see me. So if people want to come and chat about things one-to-one, we'll try that as a way of doing it rather than splitting out from the breakout room. And that means that I can see chat here and so on. Where are we? Too many windows. Right. So, week 6, interpolation methods. So this is not dissimilar in some ways to what we did last week and the assessment. So there was a whole set of data. We were doing this nonlinear, this least squares curve fitting. A curve in a general sense, a straight line is a curve in that. So we've got some linear parameters that fit some functions, and we set them up to get as close to the line as possible. I'll go through the assessment tomorrow as well. So interpolation methods, I will go into the lecture slides if no one's got any questions before we begin. So the stuff we did previously with the regression, when you tend to want to use it is when you've got lots of data, quite a lot of data points, and the data is not exact. It's got some noise on it. And what that means is when you've got lots of data points, even if you had the correct model for the data, your set of equations will be inconsistent. You've got more equations in principle than parameters. So the only thing you can do is to find the best set of parameters, get as close as possible. If you've got fewer points that you're confident on, or you just want to quickly estimate locally 0.1, 0.2, what's the value in between, then you tend to use these interpolation methods. And that's what we'll look at this week. And so in the assessment, the first question, I was looking for a solution using interpolation. It'll be a good exercise to compare it to a least squares version. So what is interpolation? So this is what I've just said. So suppose we've got some data that looks like this, so more or less as we had before. And suppose that we suddenly want to know what is the value of our function at x equals 2.5. And so, depending on the shape of the data, etc., we might want to use different methods to make an estimate of what x is at 2.5. So one approach would be to use a least squares approach like we've done in previous weeks. This week we're going to do something different, sort of more classical interpolation methods where you assume the data points are correct. You take 1, 2, 3 data points and you fit some function that will go exactly through those data points, but which will also allow you to estimate the value of the function between the points that you're given. And so the appropriate method to use will depend on how accurate you need to be and how expensive it needs to be. Sometimes you may also want your approximate function to be able to be differentiated so many times, or some other properties that you want to fit in. So sort of examples of this sort of interpolation, they come up a lot in gaming where you want to move things around. You don't want to calculate an expensive function too often, so you just want to approximate it nearby. So, the simplest case, you've just got 2 points. And if you want to find a point in between, the value of the line somewhere in between, you just work out the equation of the line in between, and then you interpolate linearly between the two data points. In general, I'll make this point now whilst I remember, it's a very bad idea to extrapolate. So whilst this point is here and this point in here, it's probably not a bad estimate of the values of the function in between. We've got no idea what the function might do outside this range. So that's why this is called interpolation. It's looking in between our data points. If you want to extrapolate beyond them, then we should probably be looking for a more sophisticated method. We'd need more data. We need to be very careful what we did. But if our data points are closely spaced, then just linear interpolation should be a reasonable approximation. We can do that very quickly and very easily. So of course, if the actual data isn't a straight line, then there's going to be an error between our linear interpolation, this approximate point here, and the exact data. So the error is going to depend on how far apart the data points are, and in principle, how far the point we're looking for is from the data points. So if it's very close to the data points, then linear interpolate. If it's halfway in between, then you're going to get your maximum error. I won't really go into the errors. It's a good idea to have a look. Normally you can make basically a Taylor series expansion and estimate the error from that. Yeah, so the thin line's the real function, and that's y equals log of x, and then we're just taking the linear approximation between the value, the function evaluated at 1 and 4. So here, hopefully these looks sort of familiar. So what we can say, one way of deriving it is to say that the slope at our arbitrary points that we want to find, our point x and its associated function value y, in between y0 and y1. So on this graph, this is y1, x1, y0, x0. Our point in between is at xy. So x and y are things that we can adjust. So we want the slope at x and y to be the same as the slope at the second data point. So they lie on the same line. We can just rearrange that, And so we've got an approximation for our y in terms of the given data points and the independent variable x. So we know y0, x1, y1, x0. The only variable here is x, so we just feed that in, and then we've got an estimate of y. You can also see that this looks like the start of a Taylor series. You've got the point that you're expanding around, and then the distance from the point, and then essentially the derivative at one of the points. So if instead of using a straight line, so thinking back to the least squares as well, you can go on and have a more complicated polynomial. So we can fit, if we've got n minus 1 parameters, so including the offset, the intercept, the linear term, quadratic, cubic. So if you've got n minus 1 polynomial order n minus 1, we can put it through n points. We could use our knowledge of linear equations. So we've got n data points, n parameters to fit, and we can use that to find the best fit, the exact polynomial that will go through the n data points. But we could also, instead of taking the full polynomial with order n minus 1 that would go exactly through it, we can restrict ourselves to a linear fit, quadratic, cubic fit as before. Again, so this is a quadratic fit. So it's quadratic that goes through these 3 data points. So you see that the fitting line goes precisely through those 3 points, and because log of x isn't actually a quadratic, it doesn't quite fit, but it comes closer than the a linear fit would do. Again, whether it's better or not is going to depend on the form of the function that you're fitting. So one way of building up this interpolation is something called Newton's divided difference. This is quite nice because it can be done sort of systematically. You can code it up in a sort of systematic way. What you do is you build up these functions, which are essentially derivatives, numerical derivatives of your data at different points. So here we've got this first order divided difference between, so the parameters that go in there, the first order are 2 points. So these are our 2 values. So this basically gives us this linear interpolation that this thing is going to be essentially the gradient evaluated sort of at those points. The same for that. And then if you want to get higher order differences, again this looks like sort of first principles differentiation. So to get the second order divided difference with 3 data points, we put the first order points on the top, and then we're dividing by the outer values there. And then the divided difference interpolation polynomial, you can write it out like this. So it's the value of the function at the first point plus the distance you've travelled, so x minus x0 times the first order term. So that's the same as we had before for linear interpolation. but then you can add in a second order term, third order term, and you can estimate the error based on the next omitted term in the series, as long as your points are fairly close together. So basically this is a Taylor expansion, a numerical Taylor expansion around some points that you've got. And to go to higher and higher order terms, you need to include more and more points in your data to be able to estimate the curvature and so on. Now there's another way of looking at this polynomial, and this will give you an equivalent expression, is so-called Lagrange interpolating polynomials. So I said this is much more the point of view of, if I've got n points, I can fit a polynomial of order n-1 through those points exactly. So this is just a recipe for not setting up the full set of linear equations, but just a clever way of writing out the polynomial explicitly. So essentially we work out what the zeros of the function should be, write them out. I don't know, maybe with maths, we might have done this with Sandro at some point. So if we add in a point, then we can get, so we've got 3 points, we can have a quadratic. So we've got 3 equations, we've got 3 points that we want it to go through, and we've got the intercept, the slope, and the quadratic term that we need to fit. So we could sort of brute force it, so we've got that goes to there. Now if we add another point, then we can get a cubic, and we could get a quartic. And what you see is we get a nice fit to the function between the values, but if we look further away, extrapolating this function based on this polynomial interpolant would not be a very good idea. And things get worse the higher order we put in. Indeed, if you go to particularly large values, things start to get quite difficult. You start to get these huge variations. You get because it's such a high order polynomial, despite it going through each of the points, particularly at the edges of the function, you can get these very weird overshoots. So it's not these Lagrange interpolating polynomials that have the full order n-1 for n points. They're nice for sort of theoretical reasons, for proving formulae, and for proving that the polynomials exist. But in practice, you're better off truncating at a lower order to avoid this sort of issue. So here's the formula for it. So what I suggest you do is you have a careful look at this formula and figure out how it works. But essentially it's a clever way of doing it. So what we do is we write out the series of points that we want our polynomial to go through. So we want it to go through y0 and at y1 and at yn. And then we write out the quotient, the two polynomials in such a way that when x is equal to x0, so the value that pairs up with that y0, this pair of polynomials will be the same, and this top and bottom will cancel and you're just left with y0. But all the other terms will include a factor of 0 and will disappear. So you see on the top of the polynomial on the top here, we've got x minus x1, x minus x2. It doesn't include x minus x0. So when x is equal to x0, we get x0 minus x1, x0 minus x2, and that's precisely what we've got in the denominator, which is x0, so the point that corresponds with this one, minus each of the other points in order. When the x, the independent variable, is set equal to x0, this top and bottom become the same, this becomes 1, but all the other terms in the numerator have got this x minus x0. So when you set x equal to x0, you get x0 minus x0, you get 0. And so all the other terms just crash out and you're just left with y0 at x0. And it's the same logic when we're at 1. This one, in the numerator, we're omitting the term with x1. So we've got x minus x0, x minus x2. But when we plug in the x1, then top and bottom cancel here, and we're left with y1. But here, all the other terms, they crash out. And in more compact notation, it's a sum, so we're adding together each of these series, and then this is the product sum, which means essentially writing out these terms. So the x minus x0, x minus x1, and we don't include the term where j and I are the same in the numerator, or the denominator, so 0. And so if you want to have a go, try figuring out the interpolating polynomial for these points. You can write a code in a loop to go through the points and to extract this thing, and you can then compare it to the Newton's divided difference. And what you should find is if you take the Newton's divided difference up to the same order, you get the same polynomial. And indeed, that you should know that the polynomial will be unique that goes through those n points. Okay. Now splines are essentially the same thing. I should have included a bit more. Look up on Wikipedia splines. They're very, very useful things. But what they're doing is essentially repeating what we've just done, but for many, many different combinations. So you've got several points that you want to plot. So you do kind of a quadratic interpolation over 3 points, then the next 3 points, the next 3 points. But you also add in a condition that the curve will be smooth and the gradient will be smooth, where these different polynomial approximations over different sets of points join up. So I suggest you have a look on Wikipedia. This isn't in the current assessment, but I probably will ask something about it in the future. So here's a linear spline. So we've got these points. So there's a linear first order polynomial between these 2 points, then it's a different polynomial between these 2 points, and these ones, these ones, these ones. So as you can see, it provides a reasonable approximation to the curve everywhere for some sort of sine function, but it has got the disadvantage that it's got this discontinuous derivative. If you go for a quadratic term, you can get them to join up and get the derivative to be continuous. And this is how Excel, for instance, draws the smooth line between points. Or if you have it directly through, it actually does this. Okay, so this trigonometric interpolation is basically the same as the least squared stuff. So this is actually something we introduced last term. Again, you can use it, and you did in the assessment, I'll talk about that tomorrow, as a way of interpolating between points. So you fit your model, and then you work out what the model says or predicts for a new set of values for the independent variable. So there's a worked example here for the trigonometric interpolation. This is for a different function. So I'm just plotting out this function. So it's this minus 1 over 1 plus exponential of x squared. So it looks like that. It's sort of upside down hat, or valley or something. And in Python, it looks a bit similar to what I had before, a bit similar to the example I put up over the weekend for doing quadratic fitting, was it? I can't remember what it was I put up. No, the exponential fit, the example. And so it's a bit like that, but instead of using exponentials, we're fitting cosines and sine functions. And then we're using that to build our Z matrix. Then we got this Z transpose Z, Z transpose Y, solving a set of equations, and then building our equations from these fitted parameters that we got from solving. And so that's our trigonometric fit to this function. And this is a term with a polynomial fit. So an interpolation, like I was talking about earlier, with 2/30th order. And you can see it's a great fit, but it's got these weird oscillations. I don't know if you can see those orange lines if you zoom in. So this one, sort of treating things in a least squared average way, tends to work better than this interpolation. Interpolation is better left to lower orders, and just a quick way of getting approximate values between points. So particularly linear interpolation or quadratics, much cheaper than doing the full trigonometric thing. We don't need to set up the matrices and solve the linear equations. You can just almost write out the answer straight away. So it's very simple, it's crude, but it's cheap and effective. And the last thing, which is in the assessment, is what happens if you've got a function of more than one variable. If our function is a variable of, I've kind of messed up. It would be better to have slightly different notation, but we've got a function, it's a function of x and y. So we could go x and y directions, and then it's different height, different color. So perhaps we've got an original image, perhaps we want to double the size of the image. So we do that, and then we interpolate the colors in between. So we got a better quality zoomed image than if we had just sort of doubled the size of the squares. How can we do this? Essentially, we do linear interpolation twice. So say we've got 4 data points. It's these red dots here. I've labelled them Q as well. So Q11, 21, 22, 12. The notation's a little bit funny. When we're using image processing, people tend to go back to using Cartesian, so X first, then Y, whereas in our code, we've always had the Y as the row index first, so just be careful when you're coding. So say we've got these 4 points. What we can do essentially is do a linear interpolation in the x direction between this point and this point to get this value r. So we do a linear interpolation here. Which gives us this expression. And then at the top, we can do the same again. We can do a linear interpolation between this point and this point to get R2. So by doing a standard one-dimensional linear interpolation between these two values along here, we can get this one and this one. And then we kind of start afresh and we do a 1D interpolation in this direction between these 2 points that we've already interpolated. So we just do 2 rounds of interpolation. And I'll leave you to try and chug through the equations, but they're just, the notation gets a bit fiddly, but that's the idea. So we've got this point and this point, we interpolate at the same y value. We just vary in the x value to get this R1, the same up here, and then we keep the x value the same, appropriate for R2 and R1 that we've interpolated, and then just interpolate in that direction. And what you end up is this equation. So with 4 terms from those 4 points that we've got, and involving the different slopes, and then how far apart the different points are. So if you follow it through what I've just said, compare those equations there, you should be able to see how it works. So this is called bilinear interpolation. It is a filter that's available for when you zoom in on some sort of image processing stuff. So there's a question just to essentially find the value p given those values in the assessment. Yeah, So the difficulty there is just keeping a track of the notation. And then you get a nice thing. So this is linear. You can do by quadratic, by cubic, whatever. Then you need more data points. So your sort of stencil would include 9 points or 16 points when you were doing the interpolation. So there's an example for you to have a little go at. I'll give you solutions to that. Have a go at trying to do it. Be careful, you can end up dividing by 0, essentially, depending on the ranges that you choose. So that's what I wanted to say on interpolation. As normal, I've glossed over some technical details, particularly the error terms and so on. I suggest you read further, have a look in one of the books, have a look online. Wikipedia is pretty good for this. Numerical method recipes, again, is fantastic, but you need to enable Flash, etc. So that's it for the lecture-y type bit. I think I will perhaps stop the recording in a second if there aren't any questions. So if there are any questions, if you think you've got a good question, it would be helpful to record. Ask it now. Otherwise I'll stop the recording, then perhaps if anything comes up later, I'll start and there'll be a separate recording, so you don't need to trawl through all of the lecture if you want to find questions at the end. Yeah, you can use any 1D interpolation method you like, as long as you explain it. I explicitly used this linear interpolation like I showed in the very first slides here, so I'd suggest you do the linear interpolation. But as long as you do something sensible and justify it, I'll give the marks, even if it's not quite what I expected. I think probably. Okay, yeah, the deadline. I will go and change that in a second. I intended the deadline to be on Wednesday, the 2nd of December, so 2 weeks today. I will adjust that deadline. That's the sort of thing Bart normally spots when I ask him. Okay, thank you. Yes, it should be the 2nd of December. I will correct that. Oops, sorry.